Hello, I'm talking to you. Today we're going to talk about evidence for evolution. In particular, we're going to focus on anatomical structures. The main idea of this section is multiple lines of evidence support the theory of evolution. So, the first piece of evidence is the fossil record. Everybody knows what a fossil is. It's one of the favorite things that elementary teachers love to teach about. A fossil is just some remains of an organism that was previously on this earth, usually embedded in some sort of hard rock. The fossil record shows relationships of ancient species to modern ones. If you dig down in a particular area or look at the edge of a cliff, the bottom of the cliff is going to have different fossils from the top of the cliff, and the middle of the cliff will probably have fossils that are kind of in between the two. So here's an example of what the fossil record shows. There's an ancient species called a glyptodont, which kind of looks like that. And we have a modern species that looks like an armadillo. They have very similar structures. The glyptodont fossils look very much like the structures, the hard, bony structures of an armadillo today. The fossil record can also show rise of new species. For example, the horseshoe crab. Horseshoe crabs you probably have seen if you've been to the beach at some point or maybe in a touch tank. They're actually more closely related to spiders than they are to crabs. Once the horseshoe crab had evolved and showed up as a new species, it didn't continue to evolve, and it really doesn't have a modern equivalent of it. So pretty much once it was evolved, it was really well adapted to its environment. So it just stayed kind of the way that it is now. So horseshoe crabs don't have a modern equivalent. They're very ancient species. So that's evidence that new species can evolve. The ancient fossils that they found as evidence of this is the same as what would be left by the organism of today. Darwin knew that the fossil record was incomplete. I often use the example that if you're making a 1,000-piece puzzle and you're missing 3 pieces or maybe 10 pieces even, you still can kind of tell what the picture of the puzzle is going to be. And that was the way that Darwin looked at the fossil record. One thing that he did, which was very interesting, is he predicted something called transitional fossils. He said, there at the bottom of this cliff, there's a fossil there's an organism that looks like this, and above it in the cliff, there's a fossil that looks like this. Somewhere in the middle, you're going to find this transitional fossil, which has characteristics of both of them. Probably the most famous transitional fossil found was the Archaeopteryx, which is the picture here in the corner. So transitional fossils are fossils that are not yet been discovered, but it's between two known fossils, and they kind of are a mashup of the characteristics of both of them. There are 2 classes of traits in fossils, and in particular transitional fossils. The first are derived traits. Those are the newfangled invention, the newly evolved traits that are not seen in its ancestors. And the second type of trait are the ancestral traits, which are, you guessed it, found in the ancestors. They're primitive traits found in past relatives. So derived traits and ancestral traits. The next piece of evidence is something called a homologous structure, and these are very interesting. They're anatomically similar structures inherited from a common ancestral species. For example, if you look at the bones here, all the green bones are all a humerus, and you as a human have a humerus as well. It's an upper arm bone. All of these bones can be found in all of these different species. Notice that they all are slightly different in each species. For example, the whale has very big radius and ulna, while the the bat has very thin radius and ulna. They've all been adapted for whatever purpose that front leg of that animal or the front limb of that animal needs it for. If you tried to swim with this thing, it probably wouldn't happen. But a whale can push large amounts of water, a lot of heavy water, with their front limb. And notice the mole back here. It actually has 6 fingers. These little orangey colored, they're carpals and they're metacarpals and phalanges. So they have 6 fingers while we only have 5. Better, the mole is more adapted for digging things. So those are some homologous structures. They're similar structures in a lot of different species, and the reason that they have them is because even though they're very unrelated today, they had at one time in their past a common ancestor. So the example that I use is the same bones that are found in a human, a bat, a bird, a whale, a salamander, a crocodile. They're the same bones. They've just been adapted for whatever environmental stresses the species needs to meet. The next type of structure is a vestigial structure, and these are very interesting. Vestigial structures are structures found in modern species that don't really have a function, or their function is very, very reduced. And the reason that the modern species has it is because these structures did in fact have a function in ancestral species. So the structure is reduced or no function in modern species, but had a function in its ancestors. An example of vestigial structure is wings on a kiwi bird. Kiwi bird is right here. It is one of those weird Australian animals that don't appear anywhere else on Earth, and apparently it didn't need to fly, so it lost its wings. But it still has some bones in there, but it doesn't actually have wings. Snakes have pelvis, and it's pretty well known that the snakes have no legs, so why would they need a pelvis? Because their ancestral species had legs, and then as they evolved, they know it was better for them not to have legs so that they were able to survive better. The human appendix is also another vestigial structure. Human appendix is very interesting because this is kind of left over from when our ancestral species ate a very unprocessed diet, a lot of grasses, a lot of seeds and things like that, which are very, very hard to digest. So the appendix portion of the large intestine was it used to be used to help digest these hard to digest things. Another example of vestigial structure in modern humans is a wisdom tooth. And a lot of people have trouble with their wisdom teeth. They are notoriously badly behaved. This one happens to be losing its sense of direction and it's pushing forward. Oftentimes people, you don't get your wisdom teeth until you're in your late teens, early 20s in most cases. Some cases they never come in. But this little wisdom tooth down here at the bottom is very ill behaved, and that one will have to be taken out because it's pushing all the other teeth forward. The reason we have wisdom teeth is because back when we didn't have good dental care and we ate a very coarse, rough diet, you probably would lose quite a few teeth by the time you were in your late teens and early 20s. So it was really important that you had a few extras in there. And an analogous structure is another anatomical structure that has to do with the function of the structure. Analogous structures are structures found in 2 very different species with very similar function, but they don't have a common ancestor. For example, wings on a bird and wings on a bee both were have evolved because they needed to fly away from something, or they needed to be able to find something and travel great distances in a short period of time.